Okay, good afternoon, everyone.
Good afternoon.
Okay, so I'm gonna start. I hope some other people will join along the way. Okay, so I'm gonna discuss quiz 29 and quiz 30.
Okay. I have just a quick question. Can I just
Yeah.
ask questions along the way, or do you want me
Yes,
to wait
please.
until the end of the lecture?
No, it's fine. Actually, I chose my own questions, but these might not be your questions of interest. So if you have specific questions you want me to discuss, that's fine.
Yeah.
Instead of me going over the questions that I chose myself, you can
Okay.
just ask me.
Okay. Thank you.
Okay. Okay. Okay, so I chose maybe I think like three questions in quiz 29 and I'm gonna go over those, but if you have any other specific questions, I'm happy to go over them. Okay, so question 13, we want to find the limit of this function, and I think quiz 29 is all about L'Hopital's rule, so you should be able to know when to use L'Hopital's rule. So the first thing, whenever I have a limit like this, I first substitute the value that is given inside the function and I see what I get. So when I substitute 0 into this function, this is 0, tangent of 0 is 0, so that is 0. So this guy is 0 over, when I substitute 0 here, that's 0, sine of 0 is 0, and this is also 0. So whenever I have a case like this, 0 over 0, for example, then that calls for L'Hopital's L'Hopital's rule. And what L'Hopital's rule says is that when you get a case like this, or it can be infinity over infinity, or negative infinity over infinity, or negative infinity over negative infinity. So when you get any of those cases, you take the limit of the derivative of the numerator and the derivative of the denominator. Just as a reminder, remember we are not taking the derivative of the whole function using quotient rule. No, we just take the derivative of this and the derivative of this independently. So this becomes the limit as x approaches 0. When I take the derivative of the guy on top, the derivative of 6x is just 6, and then minus 6 secant squared x, that is the derivative of tangent, then over the derivative of 3x is just 3, then minus 3, the derivative of sine x is just cosine x. Okay, after taking that derivative or those derivatives, once again I take the limit and I see that when I substitute 0 wherever x is, secant squared of 0, that is 1 over cosecant squared of 0. And cosecant of 0 is 1, so the whole of this guy becomes 1. So this is 1, so this is 6 minus 6, and this is also 1. And we see that once again, we get 0 over 0. Now, again, you apply the L'Hopital's rule. So you can apply L'Hopital's rule as many times as you want until these forms disappear. Okay, so once again, I take L'Hopital's rule, so this will be limit as x approaches 0. When I take the derivative of 6, that is a 0. Okay, then minus, I need to take the derivative of this guy here. So this will be 6 is a constant. The derivative of secant squared, that is 2 secant x, right? I'm using chain rule, so the 2 drops, reduce the power by 2, I just remain with secant x, then times the derivative of secant x, which is secant x tangent x, then over the derivative of the denominator, that is 0 minus, when I differentiate cos x, I just get a negative sign of x. Okay, so this will be limit as x approaches 0. This will be, I can say, negative 12 secant squared x, then tangent x, then over, this is a negative times a negative, that's a positive, plus 0, so this will be just 3 sine of x. Okay, this 3 can reduce this to 4. And the best thing I can do here is to rearrange this function, so I can say this is the limit as x approaches 0 of negative 4. Now, I know that secant squared is the same as 1 over cosecant squared, so this will be over cosecant squared x, right? But remember, there is a sine x down, so I can multiply that right here. Then times tangent of x, but tangent of x is the same as sine of x, then over cosine of x. Okay, so sine of x can cancel, and finally I remain with the limit as x approaches 0 of negative 4 over cosecant cubed of x. And when I take this limit, substitute 0 where x is, cosine of 0 is 1, so 1 cubed remains 1, and this guy, the whole of it becomes negative 4. Maybe one thing I have to comment about, check that until I actually take the limit, I keep writing the word limit as x approaches something. So you have to keep writing that until you actually take the limit. Okay. Question 12, same thing. I'm taking the limit as x approaches infinity of this function. So natural log of, so I substitute infinity here. So natural log of infinity, when I take a natural log of a large number, I'll get something large. So natural log of infinity remains infinity. And when I square it, I still get infinity. And when I substitute infinity there, I still get infinity. So once again, this calls for L'Hopital's rule. Okay, so L'Hopital's rule says that I take the limit, but take the derivative of these functions independently. So when I take the derivative of natural log squared of 3x, this is the same as 2 natural log of 3x. I'm using chain rule, then times the derivative of natural log of 3x, which is the same as 3 over 3x. I hope you remember that. Now, let me remind you that natural log squared of 3x and the natural log of 3x squared are different. What we are doing is this one. This one is where you would have to drop the 2 down there. Okay, so this is the derivative of the numerator. Okay, and then the derivative of the denominator is just 6. These 3 can cancel. And if I want to write this nicely, this is limit as x approaches infinity of 2 natural log of 3x, then divide by 6x. This 2 can reduce this by 3, and I have natural log of 3x over 3x. Now, when I take the limit of this, still I see that I get infinity over infinity, and therefore I take L'Hopital's rule once again. So let me say here, I'm taking L'Hopital's rule the first time, and now I need to take L'Hopital's rule the second time, and this will be limit as x approaches infinity. I take the derivative of natural log of 3x, which is just 3 over 3x. Okay, that is the derivative of the numerator, then over the derivative of 3x, which is just 3. So this can go, and if I write this nicely, this will be x infinity of 1 over 3x, and 1 over infinity, that is just a 0. Okay, question 11, same thing. If I substitute infinity inside those 2 functions, I'll get infinity over infinity. So I'm going to take L'Hopital's rule for the first time. Now you need to be careful when we are taking these derivatives. Of course, you need to remember how to take the derivatives of the function. So if I take the derivative of the numerator, natural log of 6x cubed plus 3, the derivative of that is the same as 18x cubed x squared, then over 6x cubed plus 3. Remember, the derivative of a natural log is you take the derivative of that function, then divide by that exact function. That's exactly what I'm doing. So this is the derivative of the numerator. I need to put the limit. So this is limit as x approaches infinity, then divide by, so this is the derivative of the numerator. I'm dividing by, I need to take the derivative of the denominator, which is 3 over 3x plus 6. Okay, I hope you can see that. Let's first write this nicely maybe. So this is the limit as x approaches infinity of 18x squared over 6x cubed plus 3, then times 3x plus 6 over 3. I'm dividing these 2 functions. I'm just multiplying by the reciprocal of this one. this one can reduce this to 6, maybe. And finally, I have something like limit as x approaches infinity of 6x squared into 3x plus 6, then over 6x cubed plus 3. Okay, maybe we can try to open that up and we see what happens. So this is limit as x approaches infinity of 18x cubed plus 36x squared, then over 6x cubed plus 3. If I want, I can pull out a 3, but maybe we can skip that for now. Now, okay, let's pull out a 3 and see what happens. Just to reduce the numbers, so x approaches infinity. If I pull out a 3, then I'll remain with 6x cubed plus 12, then over 3 into 2x cubed plus 1. So I'm just reducing the numbers. Okay. Now, when I take this limit, once again, I see that when I take this limit, still I'll have infinity over infinity, and therefore I'm going to take L'Hopital's for the second time, and this will be limit as x approaches infinity. Take the derivative of the numerator, and when I take the derivative of this function here, I'll get 18x squared plus 0. Did we do? No, 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 not plus 0. So this is not 12, this is 12x squared. Okay, so the derivative of this is 18x squared, then plus 24x, then over the derivative of the denominator, which is just 6, which is just 6x squared. Once again, I can try to reduce this, so limit as x approaches infinity. I can pull out 6x, and inside I'll remain with 3x, then plus 4, and then over 6x squared. The 6 can go, and the x can reduce this x by 1. Okay. This one becomes limit as x approaches infinity of 3x plus 4, then over x. Once again, if I try to take the limit of this function, I'll still have infinity over infinity, and therefore I need to take L'Hopital's for the third time. And when I do that, I'll have limit as x approaches infinity. When I differentiate 3x plus 4, I just get a 3. And when I differentiate x, I just get a 1. And this is limit as x approaches infinity of 3. And this is equal to 3. So the whole point is you can see that we take the limit, we take L'Hopital's rule until these indeterminate forms disappear completely and you're able to get a nice limit. Okay, Saldon, is that fine?
Yes, I just have a question though.
Yeah,
Regarding the use of L'Hopital's rule,
yeah.
do we? Because I'm quite confused on where do you stop to kind of like evaluate if it's still infinity over infinity.
So you just stop. So let me see whether I'll answer that nicely. But the whole thing is at every stage. So after taking the derivative, right? And you have an answer after taking those derivatives, then take the limit of that function and you see what you get. If you take the limit of that function and you still have infinity over infinity or 0 over 0, then you continue. So at this point, if I take the limit of this, I'll get infinity over infinity. And there is no way I can factorize these two functions in such a way that the infinity disappears. So I have infinity over infinity, so I have to take L'Hopital's rule. Let me give an example. Let's say I do L'Hopital's rule the first time and I end up with a function like 2x squared plus, no, let's say 2x plus x, right? Then over x squared. Let me write that in red. This is just an example. So after taking L'Hopital's rule, let's say I end up with 2 x squared actually plus maybe x then over x cubed. And I'm taking the limit as x approaches infinity, right? Maybe this is not good. Let me set 2x. Yeah, let me set 2x over x cubed. And I'm taking the limit as x approaches infinity. Now, I see that if I substitute this directly in this function, I'll have infinity over infinity. So I would be tempted to take L'Hopital's rule. But this function, there is something I can do to it. I can reduce this x and this x so that I have limit as x approaches infinity of 2 over x squared. And now I no longer have to take L'Hopital's rule, but rather I can take this limit directly and I get a 0. So to answer your question, you continue taking L'Hopital's rule for as long as you still have the indefinite form and you cannot factorize this function in such a way that the indefinite form disappears. Is that fine?
Yes. So kind of to summarize it, I would
Yeah.
need to be using L'Hopital's rule until I get rid of the indeterminate,
Indefinite form. Yeah.
yeah, indefinite form.
Yeah.
But to find that, I would have to like it is like a cycle of like finding the derivative and then reducing it and then
Yeah.
putting in the
Exactly.
limit, and then if it does not
Exactly.
work, then I would just like do it
Exactly.
over and over again. Correct?
Over and over again. Yeah.
Okay.
Yeah.
Thank you.
Okay. Uh, if you went over quiz 29, is there any other specific question you'd want me to do?
I think I actually answered quiz 29 a long time ago.
Ah,
So
okay, okay,
yeah, I was just like catching on it because like I'm trying to focus on reviewing for the upcoming exam
okay,
that we do have. But yeah, but so far this is like a good refresher, also like a good points to remember during the upcoming test. Thank you.
okay. So I'm gonna go to quiz 30.
Oh yes, that's fine.
So quiz 30, we are still taking limits, but this is now a little different. Because of course at some point you might need to use L'Hopital's rule still, but this one now is using some tricks of taking limits, and in this quiz, we are going to have forms like let's say 0 times infinity. If you take a limit directly and get something like 0 times infinity, or you get infinity minus infinity, or you get 1 to the power 0, or you get 1 to the power infinity, maybe infinity to the power 0. So forms like this. So we need to know how to take limits of these guys, and I think I can discuss them along the way as I do some questions. But just quickly, if I have 0 times infinity, if I take the limit and I have a form like 0 times infinity, then I rewrite that function in such a way that I'll have an indefinite form, maybe 0 over 0, or infinity over infinity. And we know that when we have this form, then we can use L'Hopital's rule. So once again, if I have a form like this, then I make sure I write the function in such a way that when I take the limit, I'll have an indefinite form, or negative infinity over infinity, whatever. Same thing to this guy here. If I have infinity minus infinity after taking the limit, then once again, I rewrite the function in such a way that I'll have an indefinite form. And after having an indefinite form, I can use the L'Hopital's rule. These other forms here, I have to use the trigonometry trick, or the natural log trick. No, not the trigonometry. So I need to use the logarithm trick, where I have to use the natural logarithm for all forms that look like this. And using an example, I think I can explain how this trick works. Okay. So I chose question 10, 9, and 6. I don't know why. They just looked like they're a bit tricky. So in question 10, we have P as that limit, we have S as that limit, and we want to find the value of 7P plus 8S. So we need to first determine the P, and P is the same as limit as x approaches 0 from the right of 8x to the power x. Now, this is what I was saying. If I try to take this limit directly, then I would have 0 to the power 0. Maybe I should have added that here. So another form can be 0 to the power 0. So you can see that I'll have 0 to the power 0, and this 0 to the power 0, this is where I need to use the natural logarithm trick. Okay, and what does the natural logarithm trick say? We have to remember some things. One thing we have to remember is that when I have e to the power natural log of x, then I just get x. I hope we remember that. So that is the first step. So the first step is that P will be the same as E. Let me see. So this guy here will be limit as x approaches 0 from the right, of e to the power natural log of 8x to the x. So I'm using the fact that when I have e to the natural log of x, I just remain with x. So you can see e to the natural log of anything remains that thing. So e to the natural log of this guy here remains that guy here. So in other words, this first step here and the second step are exactly the same. I have not changed anything. Okay. I hope you can see that. Now remember I'm taking the limit, so this limit I'll bring it up here and I'll have P is equal to E to the limit as x approaches 0 from the right. So I'm just bringing this limit and I'm putting it on top here. Okay, limit of natural log of 8x to the 8x to the x. Now, you know what? Let me just put this in a different color so that you know what I'm trying to deal with. Okay, so what is most important is that we need now to find that thing in green. And I'm going to first find it separately. So I want to find the limit as x approaches 0 from the right of natural log of 8x to the x. Now, using the rules of logarithms, like I said, this x can drop here. So this will be the same as limit as x approaches 0 from the right of x natural log of 8x. Okay. Now, if I take this limit directly, then I see that I'll have 0 times 0. So now this is a form like this one here. So I'll have 0 times 0 instead of 0 times infinity. Another form we can have is 0 times 0, and that is the case. No, actually this is 0 times infinity, sorry. This is a way. Because natural log of 0 is undefined, right? So this guy is, when I substitute 0 there, I'll get 0 then times infinity, and now this brings us to this form. So you can see that in the same question, I have this form here, which required me to use the logarithm trick, and now I have this form here, which requires me that I rewrite the function in such a way that when I take the limit, I get an indefinite form. Okay. I guess I need to push this one down. Okay, so I have 0 times infinity. So what does that mean? I have to rewrite this function in such a way that when I take this limit, I get an indefinite form. And when you're rewriting this function, whatever you put in the denominator, always make sure that it is the easiest thing to differentiate. Okay. So when I rewrite this is the same as limit as x approaches 0 from the right, and this is natural log of 8x, then over 1 over, I hope you can see that. So this x here, I'm putting it down, but when I put it down, it becomes a reciprocal. Note that this function here is exactly the same as this. But now when I take this limit, you can see that limit of the natural log of, so natural log of 0 is infinity, and 1 over 0 is also infinity. So you see that we had this form here, and now I rewrite the function in such a way that when I take this limit, I get an indefinite form. I hope that is fine. Now, if I have that indefinite form, then now I can take the L'Hopital's rule. So this will be limit as x approaches 0 from the right. And L'Hopital's rule says that I differentiate the numerator. So differentiate natural log of 8x, which is just 8 over 8x. right? Then divide by, differentiate 1 over x, that is minus 1 over x squared. So this 8 is going to cancel, and if I rewrite this, I'll have limit as x approaches 0 from the right, 1 over x, then times the reciprocal, which is just negative x squared over 1. I hope that is fine. So this x can also reduce here. And finally, I have limit as x approaches 0 from the right of negative x. And when I take this limit, I just get a 0. Now, remember everything that I have worked on in green is this guy on top. Okay, I hope you see that. So therefore, my P is the same as E to the power everything in green, but everything in green has given me a 0, so this is E to the power 0, and therefore my P is equal to 1. Okay. In the same way, we need to find S, and I'm not going to continue down. I'm going to do S right here. Okay, so let's find S. So S is the same as the limit as x approaches infinity of E to the power negative 7x, then times square root of x. Now, once again, when I take this limit directly, you can see that E to the power negative infinity, that the whole of that is 0, so that is 0, then times infinity. So I still have that form, and therefore I have to rewrite this function such that the limit gives me an infinite form. So S is the same as limit as x approaches infinity of e to the negative 7x, then over 1 over square root of x. So this square root of x, I'm just bringing it down, but when I bring it down, it comes as a reciprocal. Now, when I take this limit directly, clearly this is the same as e to the negative infinity, that's 0, and then 1 over infinity, that is also 0. So that is an indefinite form, and therefore I can now take L'Hopital's rule. And L'Hopital's rule, once again, says this is limit as x approaches infinity. Take the derivative of e to the negative 7x, that is the same as negative 7 e to the negative 7x, then over the derivative of 1 over square root of x. Maybe I'll just remind you real quick here. 1 over x to the power half. Square root of x is the same as x to the power half, right? Now, I remember I can write this as x to the negative 1/2. If I take the derivative of this is negative 1/2 x to the power negative 1/2 plus 1. That is just 1/2. Okay, I hope you can see that. So this derivative is negative 1/2, then x to the power positive 1/2. Okay. Now, when you take the limit of this guy, once again, exponent of negative infinity, that is 0. And now, when I substitute infinity inside here, I just get infinity. And 0 over anything, that is just 0. So my S, so therefore, my S is equal to 0. So we have P as 1, and we have S as 0, and therefore we can just calculate this guy here. So 7P plus 8S, this is just 7 times 1 plus 8 times 0, and this is just 7. Okay, I hope that's fine. Let me go over question 9. Yeah. Okay. So question 9, we have M as that limit, N is that limit, and once again we want to find 5M plus 10N. Okay, so let's first deal with M. Now, M, check that M, when I take the limit as x approaches 0 from the right of this guy, sine 0 is 0, so this guy is 0 to the power 0. I hope you can see that. So therefore, we shall need the logarithm trick. When I take this limit, this is 0 to the power 1 over infinity, so this is also 0 to the power 0. So this guy, we shall also need the logarithm trick. Okay? So let's first do M. So M is the same as, and I'm going to use the logarithm trick right away. So this is the same as limit as x approaches 0 from the right. And we said that e to the natural log of this function, sine of 10x, then to the power x. I haven't changed anything because e to the power natural log of anything remains that thing. So I remain with that same function, okay? Now, once again, this limit, I'll bring it on top here, and I'll have m as e to the limit, and I'm gonna write, once again, I'm gonna write that in a different color. Limit as x approaches 0 from the right of natural log of sine of 10x, then to the x. Okay, so what I want to find is that thing in, is it yellow? In yellow. Okay, so let us first find that. So once again, this x can drop here, and I'll have limit as x approaches 0 from the right of x natural log of sine of 10x. Now, when I take this limit as x approaches 0, this guy will be 0. When I substitute here, that will be 0. And the natural log of sine of 0, that is actually negative. That is actually negative infinity, right? So we have this form 0 times negative infinity. That is the same as having, did I rub that? I guess so. That is the same as 0 times infinity. And therefore, I have to rewrite our function in such a way that when I take the limit, I get an indefinite form. So this is limit as x approaches 0 from the right of natural log of sine of 10x, then divide by 1 over x. And clearly, when I take this limit, I'll have negative infinity over infinity, which is an indefinite form, and therefore I can use L'Hopital's rule. Now, when I use L'Hopital's rule, this will be limit as x approaches 0 from the right. When I take the derivative of natural log of sine of 10x, remember it becomes 10 cosine of 10x, then divide by sine of 10x. That's how we take the derivative of the natural logarithm. You differentiate this guy, which you get that, then divide by that same guy, which is that guy there. So that is the derivative of the numerator. The derivative of the denominator is negative 1 over x squared. So I'm dividing by negative 1 over x squared, and this I can write it as x approaches 0 from the right of 10 cosine of 10x, then divide by sine of 10x, then times the reciprocal, which is negative x squared over, which is negative x squared over 1. Okay. So this becomes limit as x approaches 0 from the right of negative 10x squared cosine of 10x, then over sine of 10x. And when I take this limit once again, you can see that I'll have 0 over 0, which is still an indefinite form. So I'll take L'Hopital's rule the second time, and when I take the L'Hopital's rule for the second time, I'll have limit as x approaches 0 from the right. We need to take the derivative of this numerator, that is by product rule. I hope you can see that. So negative 10 is just a constant, so I can leave it the way it is. So take the derivative of x squared cosine 10x. This is the same as we hold x squared, differentiate cosine of 10x, which is negative 10 sine of 10x, then plus hold cosine x squared and cosine 10x and differentiate x squared, so that will be 2x times cosine of 10x, and that is the derivative of the numerator, and the derivative of the denominator is 10 cosine of 10 cosine of 10x. Okay. Now, I can simplify this, or I can just take the limit directly. We can see that when I take the limit as x approaches 0, this guy will be 0. So the whole of this function will give me 0. The whole of this function will give me 0. Cosine of 0 is 1, so the whole of this guy will actually give me 10, right? So when I take this limit, I have 0 over 10, which is equal to 0. I hope you can see that. So this guy in yellow, when I evaluate it, I end up with a 0. So once again, therefore, m is e to the 0, which is just 1. Okay. I need to evaluate n, and n is limit as x approaches infinity of 5x plus 1 to the power 1 over x. And once again, this is infinity to the power 0. And still we need to use the logarithm trick. And therefore, my n will be the same as limit as x approaches infinity of e to the natural log of 5x plus 1 to the power 1 over x. When I take the natural log on top, this will be e. I'm going to write it in a different color again, of limit as x approaches infinity of natural log. Remember, this 1 over x can come down here. So this will be natural log of 5x plus 1, then divide by x. I hope that is fine. If this guy comes here, then I have this times 1 over x. So that is why the x is coming down here. Now, that guy in blue, let's first work on that guy in blue once again. And when I work on that guy in blue, I have limit as x approaches infinity, right? Of natural log of 5x plus 1, then over x. And when I do that, I see that I have infinity over infinity. So I will need to do L'Hopital's rule. And when I do L'Hopital's rule, this is limit as x approaches infinity, 5 over 5x plus 1. That is the derivative of the numerator, and the derivative of the denominator is just 1. So when I divide by 1, I remain with the same thing. And when I take this limit, I see that I have 5 over infinity, and 5 of anything over infinity is just 0. Okay? So once again, we have our n as e to the power 0, and this is equal to 1. And finally, what our question is asking for is 5m plus 10n, which is just 5 plus 10, and this is 15. I really hope that's fine. Personally, as my last question, I chose question 6 because I felt like it had more tricks. So I'm gonna go over question 6. Question 6, once again, if I take this limit directly, this limit, you can see that it is 2 to the infinity, then a to the infinity. So the whole of that gives me infinity, then to the power 0. So I need to use the logarithm trick. And the logarithm trick says this is limit as x approaches infinity of e to the natural log of this same function, 2 to the x plus 8 to the x, then to the power 1 over x. When I take the limit on top, this guy will be e. Let me write it in green maybe. Limit as x approaches infinity of, remember this guy can drop here, so I'll have natural log of 2 to the x plus 8 to the x, then the whole of it over x. I really hope that is fine. So let me write that guy in green. So we need to evaluate this natural log of 2 to the x plus 8 to the x, then over x. Now, when I take this limit directly, once again, I'll have infinity over infinity. So I'll take L'Hopital's rule. And when I take L'Hopital's rule, this is limit as x approaches infinity. Now take the derivative of this function here. I have to take the derivative of this, then divide by that same function. We need to remember how to take the derivatives of this. I hope you remember that when I take the derivative of 2 to the x, I'll have 2 to the x, then times natural log of 2. Remember, let me remind you here, when I take the derivative of a to the x, then I get a to the x times natural log of a. Now remember that is because we just have x, because the derivative of x is 1. So there is a silent 1 there. In other words, if it is d dx of a to the power some function, then this is the same as the derivative of the function, then times a to the function, then times the natural log of a. I hope you remember that. So when I take the derivative of 2 to the x, I get the derivative of x, which is 1, then times 2 to the x, which is that guy, then times natural log of a, which is now natural log of 2. Okay. Then plus, same thing, this will be 8 to the x, natural log of 8, and the whole of this is over 2 to the x plus 8 to the x. Remember, I take the derivative of this, which is this guy on top, then divide by that same guy, which is this. That is how I take the derivative of a natural log. So the whole of this is the derivative of the numerator, then you divide by the derivative of the denominator, but the derivative of x is just 1. So I can just remain with that guy then. Okay. I really hope that is fine. Now I need to play around with this function. You can play around with it in any way, but I mean I can play around with it in a different way compared to what you would do, but as long as you're doing the right thing. Okay. So this is limit as x approaches infinity, and what I'm gonna do 2 to the x natural log of 2. Now 8 to the x, I want to write 8 to the x as 2 to the x. Remember 8 is the same as 2 cubed, right? So 8 to the x is the same as 2 cubed, then to the x. Now I can switch up these guys here like this, and I write this as 2 to the x, then to the power 3. It's really the same thing. So this guy, I can write it as 2 to the x to the power 3. And once again, natural log of 8 is the same as natural log of 2 to the 3. And by rules of logarithms, this can drop, and I have 3 natural log of 2. So I'm writing this as 3 natural log of 2, then divide by 2 to the x plus 2 to the x, and the whole of it to the power 3. Okay. Now I'm trying to pull out some things that are common so that maybe some things can cancel. And in the numerator, what I can see is that I have 2 to the x, natural log of 2 is common everywhere. And when I pull out that, I'll remain with 1 plus 3 times 2 to the x squared. Hope you can see that. So 1, 2 to the x came out, so that's why it becomes squared. The natural log of 2 came out too. So this is something like that. Then over in the denominator, 2 to the x is common, and I remain with 1 plus 2 to the x squared. I hope that is fine. The 2 to the x can cancel, and what I remain with is when I take the derivative, let me first write this nicely maybe. So this is limit as x approaches infinity, natural log of 2 is outside, then 1 plus, I can write this as 3 times 4 to the x, then over 1 plus 4 to the x. I hope you can see that. 2 squared is 4, but we have a power x there. Okay. Now, if I take this limit clearly, I'll still have an infinity over infinity, and therefore I need to take a second L'Hopital's rule. Now, when I take the second L'Hopital's rule, I'll have limit as x approaches infinity, right? The natural log of 2 is a constant, so I can just leave it there. Now, when I take the derivative of this guy, the derivative of 1 is 0, and when I take the derivative of this, I'll have 3 times the same way we took the derivative of 2 to the x. This derivative will be 4 to the x, then times natural log of 4, then divide by the derivative of the denominator. If I differentiate 1, I get 0. Then the derivative of this is 4 to the x, then natural log of 4. Everything is multiplying, so this guy and this can cancel with this and this one here. Okay, I hope that is fine. So finally, what do I remain with? I remain with the limit as x approaches infinity of 3 natural log of 2, which is just a constant, and this is the same as 3 natural log of 2. Okay, guess what? Once again, from rules of logarithms, I can write as natural log of 2 cubed, and this is the same as natural log of 8. Remember that answer is for this guy that we wrote in green, and therefore our limit is actually, the same as exponent of that guy in green, which is natural log of 8. Okay, and remember what we said. We said that natural log of x is equal to x. In other words, natural log of anything remains that thing. So natural log of 8 is just a. So it's a little bit bulky, but if you really know what you're doing and you make sure you don't make a mistake, then you should be fine. Is that fine?
Yes. Um, could
Mhm.
I ask for a favor if you could just like scroll up towards
Yeah,
question? I think it was question number 10 when you
10.
were finding about S, P, and S. Because
Yeah.
I just didn't catch how do you solve this. Wait, hold on, sorry.
So where do should I repeat? I'm fine to repeat the whole thing. Should I
Oh
repeat the whole thing?
no, I just maybe it was just too fast for me earlier that I didn't like kind of got into the solution of how you look for S. But
Okay.
yeah, I did.
So should I start from S?
Yeah, could you repeat it? Sorry about that.
It's fine.
Okay, thank you.
Okay, so let's rub off this S. Okay, so S, we need to calculate this limit as x approaches infinity of to the negative 7x, then times square root of x. That's what we want to find. And once again, if I take this limit directly, I'm saying that e to the power negative infinity, so e to the power negative infinity, that is 0, right? And when I substitute infinity right here, square root of infinity, it remains infinity. So this is 0 times infinity. And this is a form we said that when you have a form like this, then you have to rewrite your function in such a way that when I take the limit of that function, I get an indefinite form. And therefore, I'm going to rewrite this as limit as x approaches infinity of e to the negative 7x. So that remains on top. And square root of x, I want to bring it down. But if I bring down the square root of x, it comes as a reciprocal. So that's why I write it as 1 over square root of x. Remember, I'm not changing the function. I'm just rewriting it. So whatever you rewrite should be the same as that. And if I'm to get exactly this, that's when I rewrite the square root of x as a reciprocal. Okay. Now, if I take this limit once again, e to the negative infinity, that is a 0, then over 1 over infinity, that is also a 0. So that is what we are talking about, that you have this form, you rewrite the function so that when you take this limit, now you get an indefinite form. So instead of this form here, now we know we have this form, and this form, the indefinite form, allows me to use L'Hopital's rule. Okay. So now, since I have that indefinite form, I can use L'Hopital's rule, and L'Hopital's rule says that I take the derivative of those functions independently. So when I take the derivative of e to the negative 7x, that is negative 7 e to the negative 7x. I hope you remember how to take that derivative. Then I want to take the derivative of 1 over square root of x. Maybe let me do that aside so that I don't have to rush it. So I want to take the derivative of 1 over square root of x, but square root of x, I can write it as x to the power half. Okay, now this is the derivative of, remember when I have 1 over x to the power half, I can take x power half on top, but it goes as a negative. Is that fine? I hope so. Now I want, so which means I want to take the derivative of x to the power negative half. And using chain rule, this is the same as you drop negative half, keep x, then power negative 1 half plus 1. Negative 1 half plus 1 is just positive 1 half. So that's how I get positive 1 half. Then times the derivative of x, which is just 1. So basically, I'm saying that when I take the derivative of 1 over square root of x, I end up with negative 1 half, then x to the power 1 half. Okay, and then from here, I'm taking the limit. Let me push this a little bit. Okay. So from here, I'm taking this limit directly. And when I take the limit, unless you want me to write it there, it is negative 7e negative infinity, then over infinity. Why? Because this is x to the power. The power is positive. Remember that. If the power is negative, x to the negative half, and I substitute infinity there, I don't get infinity. I actually get a 0. because x to the negative half is the same as 1 over x to the power half. So this will be 1 over infinity, and 1 over infinity is 0. But now that the power is positive, then when I substitute infinity there, I just remain with infinity. So this is infinity, then times negative. So in fact, maybe I should be putting a negative there. I hope that is fine. So the whole answer is e to the negative infinity, that is 0, 0 times negative 7, that is 0, then over negative infinity, and that is how I end up with a 0. Is Have I tried to clarify that before I continue?
Um, you were asking if you clarified that earlier.
No, no, is that fine now?
Yeah, 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 yeah.
Okay.
I just like I just got confused by
Mm.
um the derivative of the square root and how it made that way, but it made sense now. Thank you.
Oh, the derivative of the square of this guy here.
Yeah, I just got lost.
Ah,
I was
okay.
like, yeah, because like I looked down for a bit, and when I saw like the video again, like I mean your lecture, I was like, oh my goodness, this is a lot. But it's okay.
Okay, okay. I hope
Thank
now
you.
it's fine.
Yeah.
Okay. So which means basically, so therefore my S is actually the same as that, but the question is asking us to calculate 7p plus 8s, and this is 7 times 1 plus 8 times 0, and that is how we ended up with 7. Okay. Okay. If do you have any questions you would want me to go over in quiz 30, or this gives you a clear idea?
I'm good with like the other questions.
I don't know.
Oh, I don't have any questions
Okay.
for the remaining
Okay.
one.
Okay. So I'm gonna stop here. Thank you for joining,
Hmm.
and I'm gonna post this just in case you want to go back and look at it.
Okay.
Okay.
Thank you.
Okay. Nice day.
You too. Have a good
Mm.
one.
Okay.